autonomous UAVs in different environments, right? So for example, we have seen companies like Zipline that essentially does package delivery between different hospitals using these drones, right? We have seen them applied in light shows, as well as space exploration in Mars and also videography. The thing is that if we look at all these different applications, we can see that all of them rely on at least one of these three assumptions, right? So the environment is assumed to be either static or quasi-static. Then we assume that there are not other UAVs in the environment, or if there are other UAVs, we assume a centralized or off-board planning, right? So the thing is that if we really want to push the boundaries of autonomous UAVs, we would like to relax one of these three assumptions. But first of all, let's take a step back and talk about what trajectory planning actually entails. So trajectory planning consists of the generation of trajectories that on one hand are dynamically feasible and on the other hand are collision-free. We would like to do this completely on board, in real time, and in a world that is discovered as the agent flies, right? So the agent, the drone, doesn't have a prior knowledge of this world where it's flying, right? So as an example here, I have some videos of a work I did during my master's, where essentially we had this drone that was able to fly in a completely unknown environment. The environment was assumed to be static, so there are not other agents or other dynamic obstacles moving around. We just have one drone that has to go from one point to another one, right? So here in blue you have the unknown space, and in orange you have the the occupied known space, right? And this is of course something that we deployed on hardware. Now, to relax these three assumptions, we need to start thinking about how to do this in environments that look much more like this, right? Where we have a bunch of agents, and we want all these agents to plan trajectories through an environment that contains static obstacles, dynamic obstacles, and also other planning agents at the same time, right? So, as I said, we have dynamic obstacles, all these boxes over here. We have other agents, all these arrows that you see around, and we would like to do this in a completely decentralized and asynchronous way. Great. So towards this goal, there are actually several challenges that we need to address, and all of them can be visualized in this picture over here. So in this picture, we have a drone, which is this one, and this drone needs to fly to a different part of the world while avoiding, in this case, these three dynamic obstacles, right? So on one hand, we need to decide how to encode the trajectory, right? The idea is that at the end of the day, we are going to solve an optimization problem, and we need to figure out a way to encode that trajectory in that optimization problem. The second challenge here is that we are dealing with other dynamic obstacles, right? Like these ones over here that are not known beforehand, right? So we are flying and we are discovering these obstacles as we fly. Another challenge here is that we have a limited field of view. In general, in this case, the drone is equipped with a depth camera that has, a fixed field of view, and that means that we don't see like 360 around the drone, right? So we have to deal with this as well. And finally, we want to do everything on board in a computationally constrained platform, which is quite challenging, especially if you need fast computation times, right? So this is actually going to be the outline I'm going to follow throughout the presentation, and I'm going to start with this part, right? So here we are going to talk about something called a polynomial basis, where I'm going to explain you how we derive the MIMO basis that allows us to perform this trajectory planning in a much less conservative way. Then we will start talking about how to essentially plan in multi-agent and dynamic environments, like these ones over here, with this algorithm called MADER. Then we will talk a little bit about how to do this in a perception-aware fashion, where the idea is that now you have to include as many obstacles in the field of view as possible to be able to detect where the obstacles are going and to be able to avoid them. And then we are going to talk about how to decrease the computation time and also how to ensure some constraints there. Anyway, so let's start with this first contribution over here. The thing is that probably the most common constraint that we have in path planning looks like this. We want a trajectory in red to be inside a given set that is representing the free space, right? So there are several ways to impose this constraint. The first way will be to, you take the set, which is this dashed line, and then you impose as many constraints as discretization points, right? So you discretize the trajectory, the discretization points are in green, and then you impose as many constraints as discretization points. On one hand, this is not safe because, of course, you don't know what's going on or what's going to happen between two discretization points. On the other hand, this can lead to very high computation time due to the number of constraints that you need to impose. Other option, and this is what most of the UAV literature uses, is something called the Bernstein or B-spline basis, where the idea is the following one. What you do is you represent this as a sequence of polynomials. For each polynomial, you can compute the Bernstein or B-spline basis that gives you these control points over here. And then there is a property called the convex hull property that essentially ensures that if you are able to guarantee that these 4 blue points are inside the set, then it's guaranteed that that interval, so this interval over here, will also be inside that set, right? That's something called the convex hull property, and it's a well-known property that applies to these splines, B-splines and Bernstein splines. So this is safe, of course, but of course we are taking some conservativeness here, right? So this is a little conservative because essentially we are modeling this trajectory in red using this huge set over here, right? So the question that we tried to answer here was whether or not there exists a basis that is able to generate the tightest possible simplex approximation of a given polynomial curve, right? So something similar to this, but with a volume that is the smallest one. So this is something that we call the Mimbo basis. And again, the goal will be to find a polynomial basis that forms a partition of unity. By partition of unity, I mean that all the polynomials in that basis need to be non-negative and they need to sum up to 1, right? Actually, this is the reason why this convex hull property holds. Okay, so if you do the math, essentially, you would like to go from a curve that looks like this on the left to a simplex that looks like this and that completely encloses that curve, right? So that curve in red is completely contained within that simplex. If you do this mathematically, you are given a polynomial curve, again in red, and you want to find the smallest enclosing simplex, right? So you want to minimize the volume of that simplex subject to the curve being in that simplex. So it looks super easy. Actually, this is a super hard problem because this is non-convex and you have an infinite constraint over here. I'm not going to go through all the details of this problem, but the idea is that this problem, as you can imagine, will depend on the given curve and also on its degree n. The thing is that if you do some math, you can transform this problem into this problem over here. Here, what we are doing is that we are maximizing, or minimizing the negative, maximizing the absolute value of a determinant of a non-symmetric matrix, and then we have these two constraints. This constraint over here is very easy. This one is super hard because this is an infinite constraint. You need to satisfy this constraint for all t. Again, I'm skipping all the mathematical details here, but the idea here is that this problem over here only depends on the degree n. So what we can do is that we solve this problem numerically offline, and then we obtain the solution for n equals 1, n equals 2, 3, and so on. And then online, we just use or go from here to here, and going from here to here is just a simple matrix multiplication. Okay? So this is the whole story. Now, how you solve this problem? This is a non-convex problem because of this, also because this is a non-symmetric matrix, and then you have this infinite constraint. You can leverage something called sum of squares programming, moment relaxations, and branch and bound, and essentially we were able to prove numerical global optimality from n equals 1 to n equals 3, numerical local optimality for n equals 4, and then we were able to obtain high-quality feasible solutions for any degree n. So once we have these solutions, again, this is something that we find completely offline, and then online, what you do is that you take the curve, and then you do a matrix multiplication with a matrix that you have stored before, and then you obtain this simplex, which is the Mimbo simplex, that has a volume that is much smaller than these two ones, and that is actually the simplex with the smallest volume. Okay? So now, there are quite a lot of applications of this. The reason why we developed this was because we were interested in trajectory planning, but you can also apply this to other polynomial systems, not just trajectory planning. But the idea now is that we can impose, both in position, velocity, or even acceleration space, these constraints in a much less conservative way, right? Because now we are using this simplex that is much smaller than the simplexes obtained by other bases. As I said, there are other applications, like in computer-aided geometry, rational curves. There are some beautiful geometric interpretations of this problem, and also there are also uses in some or comparisons with something called the sleeves or the sleeves from CAD. Anyway, but this part, or until now we have covered this part where the goal was to develop or to be able to obtain this simplex that encloses a given polynomial curve and that has minimum volume. Great, so now how can we leverage this to perform trajectory planning? This is something that we are going to cover now. Let's start first by thinking just about dynamic obstacles. We are not going to think about other agents, just dynamic obstacles. Okay, so there are several challenges to this. The idea is that you need to somehow impose a constraint that says that the trajectory that you want to generate is collision-free with respect to the trajectories that other obstacles are executing, right? So one way to do this will be to just impose point-wise constraints, where the idea is that you discretize the trajectory that you are going to optimize, you discretize the trajectory of the obstacle, and then you impose pairwise constraints, right? As you can imagine, this doesn't scale very well, and it becomes intractable very easily. Other option will be to rely on naive solutions, where essentially you say, okay, if the dynamic obstacle is going to execute this trajectory, or whatever trajectory, I'm going to classify all that space, all the space that dynamic obstacles is going to use, as occupied, regardless of the specific time the dynamic obstacles is passing through that point, right? So as you can imagine, this is super conservative and can actually easily lead to infeasibility. So then the proposed solution is as follows. What we do here is that, imagine you have a planning agent over here that is trying to optimize this dashed trajectory over here. And we have, in this case, in this example, just two obstacles, one obstacle over here, and then one obstacle over here, right? So what we do is we first compute an outer polyhedral approximation of a given interval of the curves. So what we do in this case, we have three trajectories. We split them in 4 intervals, right? So first interval, second, third, and fourth. For each interval, we compute an outer polyhedral approximation. In this case, this is the trajectory you are optimizing. For drones, we typically use splines. There are other trajectories, but in this case, we use splines. So we can simply leverage the Mimbo basis to obtain these outer polyhedral approximations. If you are dealing with obstacles, if they are following polynomial trajectories, you can still use the Mimbo basis. If not, you can always discretize it, compute the convex hull of the Minkowski sum, and then increase the size of these polyhedral recompositions to be able to take into account this error, right? Either way, you obtain a polyhedral decomposition for each interval, both of the planning agent, the trajectory of the planning agent, and the obstacles. Once you have that, the only thing that you need to do is that you need to impose linear separability between every pair of polyhedra, right? So for example, this plane over here will separate this polyhedron with this polyhedron, right? Then you will find another plane that will separate this polyhedron and this polyhedron over here, and so on, right? So this goes with this, and this goes with this, and then the second, the third, and so on, right? So of course, this is just a 2D example. This is an algorithm that was designed to work in 3D, and this is a 3D visualization. This is the trajectory that the obstacle is following, is executing, and then this is the trajectory that we are currently trying to optimize. The idea is that it's the same one, but in 3D. What we do is we split it in several intervals, in this case from 0 to 6, 7 intervals, and then we compute an outer polyhedral decomposition of the first interval, second interval, fourth, third interval, and so on, both for the obstacle and for the agent. And then we obtain a plane that separates these 2 polyhedral decompositions. So if we write down the math, it looks something like this. I'm not going to go through all the details of this optimization problem, but the idea is that we want to maximize the smoothness of the trajectory. This is the first term. Then we want to include some kind of penalty for the end location of the trajectory, and then we have these initial and final conditions, the collision avoidance constraints. This essentially says that there exists a plane between every pair of polyhedra, and then we have these constraints over here that encode the dynamic limits of the drone, right? So the problem here is that both n and q are decision variables, so you can clearly see that this is a non-convex problem. If you have a non-convex problem, you need an initial guess. There are many ways to obtain this. What we did for this case was to design an algorithm called octopus search, which is essentially a variation of A star, but that is able to operate directly with the control points of the spline. That means that by construction, this algorithm, this initial guess, is going to be smooth and is going to satisfy as well the dynamic limits of the UAV. Moreover, every time you take a step in this A star search, you solve a linear program, an LP, to be able to find these planes, which is actually another decision variable, and that you will need also for the initial guess. Okay? Great. So let's jump into simulation. So this is something that we implement it in code in C++, and then we run different simulations over here. So here you have a single agent moving and flying in an environment that contains 50 box-like dynamic obstacles, and here you have another example with more complex obstacles, right? Heterogeneous obstacles over here. Again, this is something that is run completely in real time. This is not something that we run, we store the data, and then we plotted it. This is something that you can visualize it as it runs. Great, so far we have talked about how to perform or how to do trajectory planning in this setting where we have just dynamic obstacles. What happens if now we have other agents? There are several ways or several challenges that appear as soon as we start thinking about multi-agent trajectory planning. And these challenges appear because we want this algorithm to be completely decentralized and completely asynchronous. By decentralized, I mean that every agent will trigger the replanning step at its own pace, right? So there is no replanning, so there is no like an ad hoc replanning status between different agents, right? Each agent is just triggering the replanning as whenever they want, right? Or whenever they want. We also want this algorithm to be completely asynchronous, right? So which means that there is, sorry, I mixed these two things. I want this algorithm to be asynchronous, which means that we don't want to impose any ad hoc dependency between the replanning status of different agents, and then I want this algorithm to be decentralized, right? Because we don't want like a centralized agent that is going to compute all the optimization at the same time, right? So centralized without a centralized agent, and asynchronous, each agent will trigger the optimization whenever they want, right? So these are the two conditions, or the two conditions that we wanted to impose in our algorithm. Now, there are several ways to do this. Here you have like a list of different state-of-the-art approaches or works, but again, the idea is that we wanted to create an algorithm that is both decentralized and also asynchronous. Now, this is a little bit tricky because essentially you need to ensure safety in a setting where other agents are planning and replanning trajectories all the time, right? And you actually don't know when they are replanning a trajectory or how long that it's going to take them. They are just going to let you know that they have replanned a trajectory. They will send you their trajectory, but you don't know how much time it took them to compute that trajectory. So the proposed solution is as follows. Like imagine we only have two agents, like in this scenario over here. What we do is we divide or we split the replanning steps into 3 steps: optimization step, check step, and recheck step. Now, the idea is that agent A will start the optimization. So at this moment, agent A will take the trajectory that agent B is executing and will include it as a constraint in the optimization problem, right? So this trajectory over here in blue is the trajectory that agent B is executing at this point, right? And agent A will start the optimization. Now, agent B, for whatever reason, is able to start the optimization and do all the steps and commit to a new trajectory here, right? So that means that agent B at this point will change the trajectory, and this trajectory will not correspond to the trajectory that was included in the constraint. That's the reason why the agent A will have to do a check step, where the idea is that it needs to compare the optimal trajectory it has found in the optimization and check it against the trajectory that agent B found at this point, right? If there is no collision between these trajectories, then it can move forward to the recheck step. If there is a collision, this optimal trajectory is completely discarded, and then we start another optimization again, right? In this recheck step, what we do is simply we check whether or not there were trajectories published in this check phase, right? We implement this as a Boolean comparison, and that way we can assume that there are no trajectories published within this step, because if not, you end up in an infinite loop. Great, so with this, we run quite a lot of comparisons that I'm not going to explain, but the idea is that we developed this algorithm in such a way that was decentralized and asynchronous, and then it was able to either equal or even outperform some other algorithms that are either centralized or asynchronous. These are some simulations that we run. Here you have 16 agents that are planning trajectories in this environment where you have 25 static obstacles and 25 dynamic obstacles. And here you have an example where you have 32 agents in a spherical configuration, right? Great, so with this, we moved and we implemented this on hardware, and here most of the credit goes to Kota Kondo, with whom I have worked quite a lot over the past years. But here we implemented that algorithm, in hardware with 6 agents, no dynamic obstacles, 6 agents, 2 dynamic obstacles, and 4 agents and 2 dynamic obstacles. Great, and with that, we finish this second part where we have talked about how to impose or how to be able to plan trajectories in settings where we have dynamic obstacles and also other planning agents. Now, there is a caveat here. In this algorithm, we assumed that we had access to the future trajectories that the obstacles were going to execute, right? In the real world, this is not the case, right? You have a dynamic obstacle, a robot or whatever, and you don't know a priori what trajectory that robot is going to follow, right? And that's where perception awareness comes in. The idea now is that you need to plan a trajectory to avoid the obstacle, perfect, but also you need to predict where that obstacle is going. So you somehow need to maximize the presence of that obstacle in the field of view of the camera, right? It doesn't make sense that you have a dynamic obstacle over here and then you keep looking at this direction, right? You need to somehow track that robot or that obstacle to make sure that it's not going to collide with your trajectory. Right, so again, the idea is that we have, and we go back to this picture that I explained to you at the beginning, where we have an obstacle, sorry, 3 obstacles, we have an agent, and we want this agent to plan a trajectory through these obstacles. Now, we don't know the shape of the obstacles, and we don't know the future trajectories of these obstacles, right? So that means that we need to leverage the trajectory that we are planning to make it easier to detect these obstacles in the camera, right? There are different ways to do this. At the end of the day, the drone will only have 4 degrees of freedom, so translation as a function of time and yaw, and you can decouple translation and yaw. So for example, you first solve for translation, and then you fix translation and solve for the yaw angle. So this is fast in the sense that it has low computation times, but as you can imagine, it's quite conservative because you are not allowing the optimizer to modify both translation and yaw at the same time, right? So you are just doing coordinate descent instead of just moving along the diagonal. So the other option is to jointly optimize translation and yaw, which is much less conservative, but of course comes at the cost of large computation times. So then to be able to do this in, that achieves less conservative behaviors, but with much less computation times, what we proposed was to leverage something called the Hopf vibration. This is a mathematical element that I'm not going to explain super in detail here, but the idea is that this is an element over here that essentially takes a fiber in S3 and maps it to a point that is the rotation according to these 2 quaternions. At the end of the day, what this means essentially is that we are decomposing the whole rotation of the drone in 2 rotations. That one that will align this blue vector, so the perpendicular to the chassis of the drone, one that will align this vector with the total thrust of the drone, and then another one that will simply rotate the drone along this vector, right? So with these 2 rotations, essentially, you can model the whole rotation of the robot. The good news is that with this Hopf vibration, the differential flatness constraint that drones have, you can essentially drop it because you know for sure that this constraint will always be satisfied, right? So that's where all these advantages comes in, right? Because of using this vibration, you know for sure that for any quaternion that you put here, once you perform these 2 rotations, this drone will satisfy these constraints, right? So the architecture then looks like this. We have the point cloud. We perform clustering in this point cloud. Then we assign an ID to one of these to all these clusters, and then we, with all the different positions where all these clusters have been, we predict the future trajectories of these clusters using these tracks that we store, right? So here there are quite a lot of methods. We use a very simple one. There are better ones. The algorithm that we use here was just cluster and then Hungarian algorithm to be able to select or to point an ID to its different cluster. Either way, you obtain a prediction of the trajectories that the obstacles are going to execute, and then what we do is similar to what we did before. We run octopus search algorithm to obtain the guess for translation and for the planes. Then we run this graph search algorithm. This is something that was not before, to obtain the yaw guess. And then with all the guesses, we input them into an optimization where both translation and yaw are completely coupled, right? And this allows us to obtain the trajectory both in position space and also in yaw space. The optimization problem looks like this. So this optimization is the one that goes here. We want to maximize the smoothness or minimize the jerk, whatever, of the trajectory. So the jerk in position space and the acceleration in yaw space. We want also, or we have also this perception aware term, where the idea is that we want to maximize the presence of an obstacle in the field of view of the camera. This is this term over here. And then at the same time, we want to minimize the blur in the image, right? So we include this term over here to minimize the projected velocity of the obstacle in the image plane, right? This is, again, with the goal of minimizing the blur of the image. And then we have these initial and final conditions, the obstacle avoidance constraints, and then the dynamic limits. Okay? So very similar to what we had before, with the exception of this term over here. Great, so I'm going to skip all the simulation results. I'm going to jump directly into the hardware results. So I'm going to show you a video in the next slide, but the idea is that in this video, you have this agent in blue that needs to avoid these 1, 2, or 3 obstacles, depending on the experiment that we are going to do. And the goal or the idea is that this drone doesn't have a prior knowledge of the shape of these obstacles, and it doesn't even know the future trajectories of these obstacles. All the computation that you are going to see here is going to happen in the computer that these drones have. So we are not going to leverage the motion capture system that this room is equipped with. And the only sensors that we want to use here are a depth camera that is going to point forward, monocular camera is going to point downwards for VIO, and then an IMU. Those are the three sensors that we are going to use. Okay? So these are the experiments. In this first experiment and the second one, we use just one obstacle, and then we start increasing the number of obstacles. Again, the idea is that this drone doesn't know where these obstacles are going, and all the computation, so perception, planning, control, state estimation, and the optimization and everything is running completely on the computer of the UAV, right? Here you can see in green, on the top left, the field of view of the camera, and here you have the onboard camera. So this would be the depth camera in RGB only, and then you have the camera that is used for VIO here on the bottom right, right? So here, experiment 7, we already have 3 obstacles, and so on. So here for the depth camera, we use the real sense that I guess many of you already know. And then the computer that this drone right now has is an Intel NUC. We have used other drones, other computers, sorry, for the drones, like Jetsons and so on. Yeah, but in this case, we use an Intel NUC. Great, so with that, we finish this third part where we have talked about, how to maximize the presence of an obstacle in the given field of view so that you plan a trajectory not just to avoid an obstacle, but also to be able to know where these obstacles are going. Great. Now, this algorithm Panther worked pretty well, but it had some disadvantages, right? So on one hand, the solutions were a little bit conservative, and on the other hand, the computation time was a little bit high. So in this fourth part, what I'm going to try to explain is like different ways that essentially we're able to achieve a computation time much shorter and then a conservative level also much smaller. Right? So the idea is the following one. If we plot what Panther, that's the previous algorithm, was what Panther was able to achieve, we had this plot of replanning time versus cost, right? So if we plan different replanning steps of Panther, the results are all these dots over here. Now, the question is, can you go to an area that has lower cost? The answer is yes, and this is actually pretty easy in the sense that you just need to optimize more variables instead of leaving them fixed. You introduce them in the optimization, and then you run, as this is a non-convex problem, you run many different initial guesses, and you take the best one, right? So we go from this area of the plot to this area of the plot. We have been able to decrease the cost, of course, at the expense of computation time. What we tried to answer here was whether or not we could operate in this area, right? Where we have a cost that is similar to this one, but with much less computation time. Okay? The proposed solution is based on imitation learning, where the idea is the following. So we use this Panther star, which is the modified version of Panther, as the expert, and then the student will be simply a neural network. And this is something that we train using Dagger. Great, so for the state of the actions, the observation will be the state of the UAV, the goal, the predicted trajectory, and the size of the obstacles. Again, these two ones could be guessed or could be obtained directly from an algorithm that we already have, or we could assume that we had access to them. Either way, these two ones are going to be two of the inputs that we feed the neural network with. In terms of the action, we want to plan trajectory, so that means that the action is going to be the control points of that trajectory. The idea is that the first control points, the ones in yellow, are completely determined by the initial conditions. The last two control points are determined by the final conditions, right? So that means that you only need to use the blue control points at the action or the output of the network. So that gives all this action over here, and then you see this index K over here, which is going to represent the set of trajectories. And this is something that I'm going to talk about now. The idea is that imagine that you have an obstacle over here, and then you run an optimization to go from this point to a point that is beyond the obstacle, right? Or behind the obstacle, sorry. So depending on the initial and final locations, you may run into just one locally optimal solution, two locally optimal solutions, 3, 4, and so on, right? So the idea is that, okay, if this is the expert, right, if this is what the optimization is saying, how can we create a neural network that produces 1, 2, 3, or 4 different trajectories, depending on its case? In other words, how can we create a neural network that is able to encode this multimodality of the problem? So the approach that we propose is as follows. The idea is that we take the observation, we pass it through the student, and then we pass it through the expert, right? The expert is just an optimization. The student is going to be a neural network. The student will produce these trajectories. The expert, Panther Star, is going to produce these trajectories. What we do here is we compute these cost matrices, both in time space and in position space, that essentially each cell of this matrix will measure the distance in these two spaces between one student trajectory and one expert trajectories. Once we have these cost matrices, we can obtain an assignment matrix that essentially will map which expert trajectory corresponds to which student trajectory, right, with a 1. And this assignment matrix is the one that is going to be used in the cost when training this neural network. Now, of course, the question here and the tricky part is how to do this. How to go from the cost matrices to the assignment matrix. There are many ways to do this, and I'm going to explain all of them. I have tried to summarize them over here, but the idea is that most of them rely on something called the winner-takes-all approaches. There are different variants, but essentially they run either into equilibrium issues or even on mode collapse issues, right? So equilibrium issues means that imagine that you have an obstacle, first you try to go right, then you try to go left. In the equilibrium, you try to just go through the center, right? Which is catastrophic in the case of obstacle avoidance, right? In mode collapse issues, you just always go right. This is kind of the idea. So to be able to address these problems, we propose a different algorithm that, again, this is something based on the Hungarian algorithm. And essentially, it consists of assigning a different student trajectory to its expert trajectory, right? So if you do this while minimizing the assignment cost, of course, then you address and solve, in most of the cases, these two issues that you have over here. These are the matrices that you obtain, but again, this is something that you can look in the paper or ask me after the presentation. For the trajectory, I haven't explained it, but there is a closed form solution. Once you have the translation, then there is a closed form solution for the trajectory that maximizes a given feature in 3D. Right, so how do we train this? So for training, in this case, this is just a static environment. We collect a bunch of expert demonstrations, we place the obstacle, and then for a given initial and final position, we obtain all the locally optimal trajectories that optimization finds, right? And then we train the network, and then we deploy it, right? So in this case, here you can see the different trajectories generated by the network directly. I'm going to skip this figure over here. Essentially, it shows that we were able to obtain at least one collision-free trajectory per replanning step. The most important one is the one over here, right? Where I explained at the beginning that we wanted to go from this area to this area over here. And now the good news is that Deep Panther, which is the name of this algorithm, is operating in this area. Here we have a cost very, very similar to the one we had here in Panther Star. The good news now is that we have a computation time that is much, much smaller. In dynamic environments, what we did was we randomly used an obstacle over here with this trajectory. This is a trefoil knot trajectory, and then we randomly deployed it in the environment and collect a bunch of expert demonstrations, right? We train a network with it, and then we did the deployment in environments that contain static obstacles, square obstacles, or obstacles that follow this square-like trajectory, eighth-like trajectory, and then an epitrochoid as well, right? Together, of course, with the trefoil knot, which is the one that was included in the training set, right? The idea of this experiment was to show that our algorithm was able to somehow generalize beyond just the environment in which the obstacle was following a trefoil knot trajectory, right? Because all these trajectories are something that the agent or the network never saw during training. Great, so far what we have been doing, and let's take a step back, what we have been doing so far is that, we have an optimization and we want a network to learn somehow the optimal optimal point of this optimization, right? So we want this trajectory to be as close as possible to these trajectories. There is one caveat here, right? So in this optimization we have some constraints. Those constraints are not guaranteed to be satisfied by these trajectories. Okay, these trajectories may be super similar to these ones, but still in that case, you are not guaranteed, or these constraints are not guaranteed to satisfy all the constraints, right? So the question is, how can we guarantee constraints when using a neural network? The idea is as follows. Imagine that you have a neural network, you input something here, and then you get y as an output, and you want this y to be in a given set. In this work, which is called Regen, we focus on convex sets. We will focus on more complex ones, but then you have to be very careful with computation time. Here I'm just going to focus on convex constraints. The idea is that imagine that this is a convex set. What is a convex set? In general, it could be defined as a combination of all these constraints, right? So you can impose linear constraints, both equality and inequality constraints, quadratic convex constraints, second order cone constraints, and linear matrix inequalities. This is actually something that just writing this one would have also been fine, because this one is a generalization of the previous ones, and this one is a generalization of the two previous ones, and so on, right? But here we just wanted to write down all of them, because if you write down all of them and then you use a different algorithm for this one than for this one, then you obtain some computational advantage. Either way, the idea is that you want the output y to satisfy all these constraints, right? Imagine that I give you, 4 constraints, one of this one, one of this one, one of this one, another of this one. I want y to satisfy all those 4 constraints, right? There are different ways to do this. In the state of the art, if you only have this constraint over here, there is something called the barycentric coordinates that you can leverage to do this, that you can leverage to be able to accomplish these constraint guarantees. Now, this solution over here, again, works only for linear constraints and doesn't scale at all. As soon as you have, or you operate in a 10-dimensional environment, then this solution doesn't, or is not going to behave well. Other option will be to, you just penalize the violation of the constraints. As you can imagine, this doesn't guarantee any hard constraint, right? In the sense that you can essentially penalize the distance between this produce point and the set, for example, but you don't have guarantees at testing time that output will satisfy that constraint. And then another option will be to perform an orthogonal projection or to perform inner gradient descent steps. Either way, the idea is that these two methods over here end up solving another optimization problem. But the whole premise here is that we are using a neural network to avoid solving an optimization problem, because it's computationally expensive, right? So if to be able to impose the constraint here, I'm going to add an optimization problem, this doesn't make a lot of sense, right? And I mean, this is something that can be done, especially for convex constraints. There is something called implicit layers, where essentially you backpropagate through optimization problems, okay? So it's well studied and it works, but again, it works at the expense of high computation time. As you can imagine as you can guess throughout the whole presentation, we are always talking about computation time, because especially for robots, this is probably one of the most important things, especially when you are trying to run all these things on board, on the robot. Great, so the proposed solution here is as follows. So imagine, just going to simplify everything a lot. Imagine that you have only a quadratic constraint, the ellipsoid, and a linear constraint, which is going to be this red polyhedron, right? So that means that the feasible set is going to be this orange area over here, and what we do is as follows. So we compute offline an inner point of the set, that's z naught, So this is going to be an inner point of the set. And then online, what we do is we let a latent variable of the network to be this V step, right? So this V is going to be a latent variable of the network. Right? That V, together with Z0, is going to define Z1. So Z1 is Z0 plus V. V is just going to be the step. And then what we do is, if Z1 is inside the set, we leave it as it is, because we already satisfy the constraint. If Z1 is outside the set, we project it back. Now, the good news is that this is not an orthogonal projection. If you want to do an orthogonal projection there, you are solving another convex optimization problem, and this is not going to be computationally tractable for robots, right? The good news is that this is going to be just a projection along a given direction. And for that, you can compute closed form solutions that I'm going to explain later. Okay, so the idea is that you have the neural network, you produce this step, V, and then you use this formula over here that essentially is projecting it back along this direction to make sure that it lies within the set. This is a 3D representation of the same idea, and there are the two challenges here are, on one hand, if you have linear equality constraints, essentially you are reducing the dimension of the space, right? So here, imagine that you have three constraints: quadratic constraint, this ellipsoid over here, linear inequality constraint, the polyhedron, and linear equality constraint, the plane, right? So the feasible set is just going to be this part over here, which is contained within the plane, right? So the dimension, the effective dimension is just 2, not 3, right? So what we do here is something called the null space matrix. This is basic linear algebra, but the idea is that you transform everything to this 2D plane, and then you lift it back, right? Using this null space projection matrix. So that was not very difficult. The difficulty comes here, right? The idea is that at some point, you need to compute the distance between an inner point of the set and the intersection between the ray that starts at that point and that follows a specific direction, right? So you want to compute, in all these examples, the distance between the orange point and the blue point, in all these examples, right? So for this case, the linear case and the quadratic case, you can easily compute it. For these other cases, especially for the semi-definite cone, is not something that is super trivial, but for this we derived a closed form solution. The most complex one, essentially you need to compute an eigenvalue decomposition, but you can easily backpropagate through that as well. So then essentially you obtain a formula that allows you to get this distance between an inner point of the set and the frontier of the set along a given direction, right? So how do the results look like? The idea is that here we randomly put an input here, so just a random input, and then you can also, if you want, randomize the weights, and then you just plot the output, right? And we do this for different sets, and you can see that in all the cases, we are guaranteed to satisfy the given constraint, right? The more general case is this one, a polyhedron, an ellipsoid, second-order cone, and PSD cone. All these examples are either 2D or 3D, but this works for any dimension, right? We even tried 10,000 dimension or more. Okay, so now let's go back to trajectory planning. How can we use this for trajectory planning? The idea is that essentially in trajectory planning we have something called the safe corridor, here in green, that represents essentially the free space. So we want to obtain trajectories that are completely contained within this free space. The idea is that all these polyhedron are linear inequality constraints, so you can impose them in the neural network using this algorithm that I have just explained. And you obtain these trajectories in 2D or in 3D that are guaranteed by construction to satisfy these constraints. We also compared against other different methods, like all these ones over here, like some methods that add al penalty, some methods that take inner gradient descent steps, like DC3, and other methods. But the idea is that this algorithm, because of the fact that we derive these distances, is way, way faster than other state-of-the-art methods. Great. So then what we did was to deploy this on hardware. So here for this, we use Animal D, which is this robot over here. We did it in simulation and also in the real world. Here, what we did was to jointly impose different constraints that are super important in this kind of robots, right? So we impose individual joint torque constraints, the sum of all the absolute torques, which essentially represents or is proportional to the current draw by the motors. Then we also included the sum of the absolute torques per leg, which has to do with the limit in the power cable that we have in each leg of the robot, and then the torques squared that has to do with the motor temperature. So these are 4 variables that are extremely important to monitor whenever you are moving these kind of robots, and you want the policy to be able to satisfy by construction all these constraints, right? So essentially, if you do the math, you end up that you can very easily show that these constraints are either linear or quadratic, right? So again, convex constraints, you can use the framework that I have just explained, and then you obtain these plots over here, right? Where you show that for any input that you have of the neural network, the policy will produce an output that will satisfy all these torque constraints over here. Great, and with that, I finish this part where we have talked about learning-based planning and how to impose constraints on neural networks. There are other projects I have worked on that I haven't covered in this talk. I'm happy to take questions at the end, but the idea is that, I work on the DARPA sub-T challenge that I guess many of you are familiar with. The idea of this challenge was to deploy a team of robots underground, like these two images, for example, are from one of the experiments that we did. This is 200 meters underground in West Virginia. And the idea is that you don't know, or you don't have a prior map of the mine. These robots were deployed in mines, and then you wanted these robots to completely explore the map, the mine, and to report the location of some artifacts with respect to the entrance of the mine with an error of less than 0.5 meters or something like this, right? So the idea is that you had these robots, they are moving around, and they are sharing their current maps to obtain a global map that is sent back to the station. You can see here that the conditions are probably the worst ones that you can find in robotics. You don't have GPS, everything is super dark, there is a lot of dust, there is a lot of mud over here, so you are dealing with all these problems when having to deploy these robots, right? I also worked on this project over here where we have a hexacopter with some motors that are a little bit tilted. That means that the drone can move like this. It doesn't have to pitch down or roll sidewards to be able to move forward. So that means that you can use it to be able to pick and drop stuff. I have also worked on continuous state estimation, where the idea is that instead of estimating discrete variables, so a trajectory just at discrete instances of time, what you do is that you use splines or Gaussian processes to be able to do this in a continuous way. And then also in Gaussian splats. For the Gaussian splats, I have this slide over here where the idea here is that we wanted to plan trajectory in a given Gaussian splat. A Gaussian splat, as many of you already know, is a combination or a way to represent a 3D environment, and need just a bunch of Gaussians put together, right? So, well, the video is not great in this image, but it's okay. The idea is that you model both the environment and the robot, and this is the novelty here. So we also model the robot as a Gaussian splat, and that allows us to obtain a trajectory in real time, or at least in computation times that are relatively short compared to other approaches, and that is able to move a quadruped through different parts of the environment. We implemented this on a quadruped, on drones, on manipulators, etc., right, on different types of robots. I have also worked on differentiable simulation, so how to train a robot, a quadruped, or how to make it learn to walk, just using differentiable simulation, so backpropagating through the dynamics of the robot. As you can imagine, this is something super hard to do because of the contacts that you have, because this is something that by nature is not differentiable, so you need to come up with some good approximations there. And now some projects I'm also working on have to do with visual navigation, so the idea is that you input a neural network with just an RGB image, maybe an IMU as well, but just that, and you want the drone to be able to fly, trajectories like this, right? So the drone, this is in the training process, so it's not perfect yet, but the idea is that the drone is using this image and is computing some features there and having some expressivity in the latent space to be able to come up with these trajectories that avoid the obstacles, right? So with this, I'm almost done with the talk. As Iago said, I lead this lab, the Trustworthy Robotics and an AI lab. So we are in ICAI, in Universidad Pontificia de Comillas. And there are open positions there. So if you are a PhD, a postdoc, or you want to do one of these two things, or even just a research stay, just send me an email, because we are super open to collaborate with other groups, and of course also with companies. So if you have some projects that you would like to work on, I have some really good students that can be used for this, or that we can leverage for this collaboration. And probably the most important slide is this one, even though it's the one of the last ones. So this is the people that made all this work possible. I would like to thank especially my advisor, at MIT, so John Howe, also my postdoc advisor, Marco Hutter, and then a bunch of students or now professors like Brett Lopez, Mike Everett, Victor Clem, Kota Kondo, Andrea, or Parker, that without them, I think all this work wouldn't have been possible. And with that, thank you so much for your attention, and now I'm happy to take any questions that you may have. Thank you.
Thanks, Jesus. Incredible presentation. I think we have time for 2 quick questions.
Sorry, I went a little bit over time. But
no, it's perfect. It was super entertaining. Questions?
First, thank you very much for the presentation. It was really interesting. I was curious about the part with the dynamic objects that you do not know the movement from pre-time, and you said you do the track and the predictions of it. How far in time do you need to do these predictions to be able to give this predicted trajectory to the octopus search afterwards?
Yeah, that's a really good question. I mean, that's in general, that's going to be a parameter that the user can code, in the sense that you can just use 2 seconds, 3 seconds, and so on. So that length has to do a lot with the maximum velocity that you are imposing the drone, right? Because if you want the drone to fly at 10 meters per second, then you need to somehow predict the trajectory quite a lot into the future, right? But then, of course, as you can imagine, the further you predict the trajectory, the more error you are going to have. So what we did there is essentially every time you take a step in this prediction, you somehow increase the size of the obstacle to take into account this uncertainty, right? It's a way to somehow encode the uncertainty growth that you already have. So in terms of what we did for these experiments, we were predicting the trajectories just 1 or 2 seconds into the future. But the idea again is that the drone is replanning at maybe 10 hertz or even more. So as soon as you predict this trajectory and you include it in the optimization, the drone will solve it and then we solve another optimization, right? So it's okay not to predict the whole trajectory because, yeah, I don't think it will make a lot of sense to predict the next 10 seconds of the trajectory because it's going to be crap. Yeah.
Okay, perfect,
Yeah.
thank you.
And related to this, I mean, it also depends, like for example, here we have dynamic obstacles and we don't have any prior knowledge about the dynamic of these obstacles. If you are dealing with an autonomous car, for example, that changes a lot because, for example, pedestrians more or less are quite predictable, right? So if you know the past of the trajectory of a pedestrian and there is a crosswalk here, it's very likely that the pedestrian will cross that crosswalk, right? So you have a prior information, and there are many works that have leveraged this. For example, Trajecton++ is a work done by Marco Pavone at Stanford, and then are many others that essentially are able to somehow predict this trajectory, taking into account this prior information. Yeah.
Thank you.
Some more questions?
Don't be afraid.
Yeah, thank you for the talk again. I'm also on the line of this prediction of the dynamic objects, and I was wondering which kind of assumptions, if any, do you take about the kind of trajectories, or because I've seen that they are not natural trajectories, they have some, so how do you estimate that?
Yeah, I mean, in terms of the prediction, we didn't assume or we didn't make any assumption. Now, if you ask me what kind of trajectory makes this algorithm work better, that's a different question, but I guess that's where you are trying to ask. Because, I mean, in the sense that here, the prediction or the predictor works for any trajectory that the obstacle is executed, right? So even if it's not like, you know, something super close to, like the positions close to each other, it's something more, you know, straight, it will also work, the prediction itself, okay? So now the tricky part here is how you essentially train the network for that. So what we did was we took this trefoil node. Maybe let me go back to that slide, which I don't know exactly what it will be, but let's try. Yeah, this one over here. So we trained it using this trefoil node trajectory, right? And then I said, okay, this generalizes quite well to all these trajectories. The trick here was to do the following. The input of the network is not this trefoil node trajectory per se, but a spline approximation of that trefoil node trajectory, right? So the network is having as an input just the control point of that spline, right? And that means that you can apply that spline and feed a spline to this trajectory, but you can also feed a spline to all these trajectories, right? So the input is going to be the same representation right, in terms of control points. It's true that the shape is going to be completely different, right, but the input is going to be the same type. Yeah, that said, again, this is an algorithm that works empirically and is not guaranteed to work for any trajectory that you put here. Like if you put a crazy trajectory, and especially if you increase the velocity of the obstacle, like this algorithm is not going to work, right? But this has to do also with the fact that in reality, like in the real world, it's not, you can never guarantee that at all times the robot will never collide, right? You have some probability that the robot will collide, and you want to keep that probability to a minimum. But yeah.
Thank you again.
No worries.
Right, I think we have time for one last question. So,
Questions?
who's the brave guy?
Thanks. Is there any inspiration that you've taken from the way that animals or humans navigate in environments?
That's a really good question. I mean, for this perception-aware part, I mean, we look at some examples either in the nature or, but I guess it was more in general. Like I cannot name a specific animal per se, but you know, in most of the planning instances that animals have, for example, imagine an eagle just flying around some forest or whatever, or even just trying to trap like another animal, whatever. Like it's always trying to keep that animal in the field of view. Okay, so this is somehow kind of the inspiration, but it's supernatural to take this inspiration, right? Because it's, I mean, you need to go to somewhere or avoid something. You want to keep it in your field of view to gain as much information as you want, right? Yeah. Other than that, I mean, of course, one possible way to not do perception awareness will be just to put a gimbal on the camera, on the drone, right? You just put the drone, and then you put a gimbal there that is able to move wherever, right? Or even just a 360 camera, or even just a LiDAR, right? So, of course, we could have put a LiDAR, but it's more expensive. It adds a lot of weight to the drone, so we wanted to constrain ourselves to a very complex setting, which is just a fixed monocular or depth camera, whatever, but just a fixed field of view, and you cannot rotate there. So you have to rotate the whole body to rotate the camera. Yeah, I guess that's everything I can say. We didn't have like a specific animal we took inspiration from, so I think it was more in general. Yeah.
Perfect, thanks.
Yeah, thank you.
All right, thank you very much. I
Thank
think
you, Iago.
one last round of applause for Jesus.
Thank you. Thanks.
And now we have a small catering for the social part, so I encourage to go talk with the interesting people in this room, and please get to know each other or get to know Jesus. Thank you.